Good afternoon, everyone. How are you guys doing? Let's wait a few seconds here for people to join the lecture. So how are you guys doing? Do you hear my voice? Do you see me or anyone? Okay, good. How's face-to-face back, like, lectures and stuff like that? So is everything's okay? Great, great. So for last week, labs and tutorials, any issues, any concerns, anything that we can do to make it better for you? Yeah. Okay. Was it a good kind of experience so far? Okay. So let me start sharing the slides with you and maybe start our lectures for today. And then we can do this. You can see that. Oh, yeah. If you can please mute yourself. That would be great. So you can focus on the lecture.
Matthew, mute yourself.
Okay, so we're kind of moving a little bit slow, but I don't care about the slow as long as we are kind of, building our knowledge in the principle of fluid mechanics. Today, we're going to talk about like an extension to the first part of the fluid statics. And mainly what we're going to cover today is looking at the pressure distribution in the fluids, right? So we talk about how we measure the pressure, what is the pressure last time, the variation of the pressure in the horizontal plane, in the vertical plane. And we talk like few examples to how to relate the pressure at any point in a static fluid. Remember, like, all these chapters talking about static fluids. So we don't have any shear stresses involved, like, all the element of the fluid is kind of, stagnant. So in this case, the whole fluid can be treated as, a static fluid, and then we can apply those principles that we talked about it last time. So today we're going to talk about, like, the hydrostatic forces acting on surfaces. And surfaces here is basically any element that is, we consider a solid surface for some reason is in touch with fluids, and the fluid is acting as additional forces acting on these surfaces. So these surfaces could be flat, this surface can be curved surface. And then we expand our knowledge into understanding a little bit on the buoyancy that you guys studied in the physics courses, or like, the science courses before, but we're going to expand it from a hydrostatic point of view. At the end of the chapter, we're going to talk about a bulk fluid motion, like a rigid body motion, as if we move the whole bulk of the fluids in a direction, but within the fluid itself, there's no shear stresses or a relative motion between all these particles. Okay. I mentioned to you, like, every time we are talking about, an element of the fluid mechanics subject, we are kind of targeting some of the application. And I mentioned in the beginning of this chapter, there's a wide range of application where we need to understand pressure and hydrostatic forces coming from the fluid pressure on these surfaces. Some of these example, as I mentioned, for forces on surface could be the dams, right? When we have, like, a body of water basically contained at the back of the dam in order to hold the fluid level to a certain height, and then allow this fluid to move through the turbines. But as long as we are kind of looking into the design of the dam itself, so we are kind of interested to see how much pressure forces coming from this head of the fluid, and we can consider, for example, the design of these dam, the construction of these dam, and so on. Let me just do that. Also, like, you know, other application related to fluid containers. These containers could be as huge as tanks that is storing a certain type of fluid. Could be, you know, oil tanks for oil water transportation, or for, like, you know, water tanks that is holding water in, you know, in the cities, or for any storage kind of purposes. Can also, you know, goes beyond all this application to maybe, like, you know, a glass kind of, you know, tunnel that you design for a restaurant or something, like as you see in this picture here. Okay, but all these application and many others, it's all depend. Okay, now we have the solid part of it, like we know you guys have taken mechanics 1 and 2, and then you look at the forces acting on these solid elements. How about if the fluid is involved in these problems? So we have to find out what will be the pressure forces coming from this fluid acting on these surfaces. Okay. We basically discussed, like, you know, the pressure as at an element is basically the differentiation of the force over this small area. And in order to find out basically the total force, you can see here, like, you know, basically the force here would be the, you know, BDA. If we need to find out the total force, so we need to integrate, you know, these pressure forces over there. So pressure at a point, or a very small little element, dA, is dF. But if we need to find out the total force acting on the surface, so we have to integrate these forces, or these pressure forces, over the area. You remember also that we talk about the pressure as a scalar quantity, which is acting on all direction and equal in all directions, which means that pressure is not affecting by the direction, but the pressure forces are. So if we need to find out, for example, now the fluid hydrostatic forces, okay, we need to find out the magnitude, the direction, and the line of action. Pressure forces is, you know, a normal force. So whatever the surface is, the pressure acting on this surface should be a normal to this surface, right? So we know the line of action all the time depend on the inclination of this surface, and the direction as well. We'll find out what I meant by the direction in this lecture. And of course, the magnitude will be function of this, you know, fluid property, right? So if you remember, the pressure is related to with the height of the fluid as rho GH, right? So pressure, if you remember, it's rho GH, or at the same time, it's gamma H. So gamma here is the density times the density times the gravitational acceleration, right? So anytime we are looking at the pressure at a point, we know what is the head of the fluid at this point, and we can determine what is the pressure is, okay? Before I get into the subject, I want to go through an exercise with you and just make sure that you guys understand what we're talking about here. Okay, imagine now we have a surface, and this is a flat surface. And this surface is located, you know, a distance from what we call it the free surface here, free surface of fluids. And this fluid has a density equal rho, right? Water, oil, whatever, right? But, you know, every time we talk about free surface, we mean that the pressure at this surface is atmospheric, okay? So the pressure here is B atmospheric, okay? And for engineering purposes, atmospheric pressure is always our reference, right? So in this case, you know, basically we consider the pressure at this surface is 0, right? Now let me ask you the question. The pressure at this point here, let's say call it point A. What will be the pressure at this point? Imagine this is a surface, and this surface is a horizontal, okay, horizontal flat surface, okay? What will be the pressure? Rho GH, excellent, right? How about at point B here. Same, right? C, same, right? So as long as this flat plate is horizontal, right? So the pressure at every point here is the same, right? So can I draw a pressure distribution here? So imagine now I am just taking a scale for the pressure value, which is basically here will be, sorry. This gamma H, right? Okay. So if I need to find out the pressure distribution here, so in this case, I will put like a scale for this pressure like this, but at every point it's going to be the same value, right? So if I plot the pressure distribution, almost I'm kind of drawing something like this. Right? Everyone agree here, right? So the pressure here, or the pressure forces here, is this scale here is gamma H, or like, let me just make sure that people don't confuse with the small h and big H. So this is H, so this is gamma H, this is gamma H. Okay. Have you seen this before? Have you seen this kind of, distribution of a stress before? Remember the mechanics, right? When you have a beam and has a uniform distribution of stress, and you remember like how to deal with these kind of things, it is exactly the same here, right? But the stress here is, we know that this stress or this pressure forces is coming from the fluids, right? And now if it's like, if I'm looking at these, right, and I need to find out the total forces, where do you think the total force is? So where is the total force of this? In the center, in the middle of the horizontal. Okay. There is only one condition we have to consider if I can agree with you. What condition I have to assume here if at the centroids? Yeah, I like this, right? The centroid here is you're basically the center of area, right? Because when I look at this surface, imagine I'm looking at this surface from this side here. So I'm looking in this surface like this, and I found this surface to be like this. Let's say, because it doesn't matter, if it's a horizontal surface, it doesn't mean that the area is uniform, right? If I look at it from the top, right? So maybe the center of area or the centroid could be here, right? You agree, guys? Everyone? Yeah, right. Now the total force will be acting basically on this center of area. You might see the force, the resultant force is like this, right? So this is our total force. But remember, in your mechanics, you are basically assuming all the beams that you are kind of dealing with is like, it has a width that is equal to 1 meter or like 1 unit or something like that. So most of the time you are dealing with uniform, area on the, normal to the paper, right? So in this case, it's all depend on this area here, right? So depend on the center of area. If this is the center of area, so the resultant force here, F total, will be basically acting on the center of area, right? And what will be the value here of this F total? What will be the value for this F total? The stress times A, right? Remember the distribution was, given in your mechanics. It will give you the value that is like the stress or the, the distribution weight, right? Which is, in our case here, is gamma H, right? But now if you multiply this gamma H, which is the stress times the total area, will give you basically the total, right? You don't need to do the integration. Do you need to do an integration here if you know the total area, Dozy? No, right? Because basically, if you know the total area and you know the center of the area, you can just multiply the total stress by the area, right? So there is no point of integrating here. Why? Because all the point has the same pressure, right? So if you know the total area, you know the center of the area, you can just multiply this gamma h times the area, right? So this is the area A capital, this would be, right? Let me just, just do another one here. If this surface here, the same thing, right? This is B is equal 0. This is H, right? And now I'm looking at the surface. This is the same, right? I'm looking at this surface in this direction here. Don't know if you can see, this is my eye here. And, I have something like this. So if I'm looking at it from the top, let's say it's something like this. This is the area now, okay? And the same thing when I put the pressure distribution, it's going to be the same thing, right? This is gamma H, right? So where is the pressure force, the total force here in this case? In the middle, exact, right? So if I look at this is the area, and because it's a uniform area, so this is, sorry about my drawings here. So if I look at this, and this is exactly what you were doing in your beams problem, right? So this is F total, right? Same thing, F total here is, if this is the area, it is basically gamma H times A, right? And it's just acting on the center here, and the center here because of the surface. Yes, of course, it's centroid as well, right? Centroid is referring to the center of the area, right? It just happened to be here because the area is uniform. The center of the area is in the middle, okay? And of course, you guys are aware of this in the mass. When you have a different kind of area, you can find out, the center of the area, looking at the integration and so on, which is something that we can discuss in the next few slides. But in general, it's a very simple analysis here. If we have a flat surface and it's horizontal, so it's a very simple analogy here for finding out the total resultant force. What will be the magnitude for this force? The magnitude will be basically, this is a magnitude. What is the direction of the force? This is your direction of the force. It's normal, right? We know that the pressure force is normal. And what is the line of action here? The line of action is passing through this point here. So we call this line here is the line of action, okay? So in order to determine the force vector here, we have to determine by three components. The first one is a magnitude, the value itself, the direction now, and then the line of action here is where is the point and that is acting, these forces acting on. Let's move to something else here, right? Let's move to a vertical flat surface, okay? And let's assume, of course, like now, if the area of the center, if the area is not uniform, we can do that, right? But let's, for simplicity here, if I look at this area from this direction, let's assume this is basically this is a flat surface here. Okay, now let me ask you a question. So this is a free surface. Okay, and this is all H. Okay, at a point A, what will be the pressure? Rho G the small h, right? Because this point here is far from the surface by this h, right? So the pressure here will be that value. Okay. How about point B? Greater, smaller, greater, right? So if I look at the pressure, it will be a little bit bigger, right? A bigger value. How about buoyancy here? Sorry if I sound boring, but again, okay. So it's a little bit, right? And it's gonna be equal to rho g h capital, right? So this is rho g h small. If we know this h capital, this is basically h capital. How about the pressure point at this point here? How about the pressure at point D? 0. Why? Because this is a free surface, right? So this is 0. So if I need to plot the pressure distribution, I might end up with something like this. Right? Agree with that? And why this is linear? Why this is linear? Because the variation of the pressure inside the depths of the fluid is linear, right? The pressure is equal gamma h, right? Or like, y is the pressure and h is x. So y is equal some constant times x. That means it is a linear relation or a linear, distribution, or a linear equation, right? So the pressure all the time is proportional to h, and this proportion is with gamma, which is a constant for the same fluid, right? So all this fluid is just one fluid. Okay. Now, if I need to find out the pressure at this, the total resultant force, do you think it will be at point A? Let's say point A here in the middle, right? Let's say this distance and this distance are equal. Okay. Do you think the pressure total force will be acting on A? Where do you think this pressure force? Lower than A or above A? Yeah, I don't think the centroidal triangle is the right way. Yes, it's actually 1/3 from C. Excellent, right? And this is basically the mechanics. Remember, when you have a load that is distributed in a triangle way, we took this as basically our thirds from this side here, right? Right. So it's basically like the third of 1/3 of h, right? If you remember, right? And this will be basically something like this. The total resultant force will be something. Okay. Where is this pressure force acting? Which direction? To the right, to the left? This is the line of action, right? So, right? Because the fluid is here, right? The fluid on this side of the surface. Okay. How about this part here? Do you think any pressure force is acting on this part of the surface? No. And this is very, very important. Lots of people making a lot of mistakes about this. Okay. Remember, we are dealing with the hydrostatic forces coming from the fluids. So all what we care about in this problem is the contacts, between the fluid and the surface. Any other part of the surface that is not in touch, right? Which means that in this case, this is the surface I'm talking about. This is my area, right? This is the area that I'm talking about. Okay. I don't care about this other part here, right? So these are the area where we have the fluid is acting on, right? So in this case, if this is your center of area, right? If this is your center of area, let's call it CG, for example, here, right? And why we call it G here? There is two area, like there is two center for any surface. One is the center of gravity, and one is the center of area. Does the center of area and center of gravity has to be the same exact? Why? Anyone? Yeah, what is the weight distribution? Excellent, Blasius, right? So basically, it is all depend on if this material is homogeneous or not, right? You might have a surface that is part of the surface is heavier than the other part, even though the area is uniform. So it doesn't have to have the weight distribution is uniform as well, right? Just keep this in mind, and then we'll get to this when we are talking about other things. But you know, this is your center of of gravity or center of area, and you know that basically it's going to be a point that is a little bit lower here, which is we call it the center of pressure. So we call this one here is B here, right? And this will be our total force here. Okay, and the pressure force will be acting on this point here. And if this surface is uniform, it's going to be like, you know, symmetrical type of, surface. This point here will be a little bit lower, as you guys mentioned, because basically the pressure a little bit, higher on the, in the lower half. So which means that the center, the pressure forces will be closer to, where the distribution is heavier, basically, right? So in this case, we have F horizontal here, right? So we can basically find out this resultant force here, right? So how about like, if we have, and again, like, you have seen in your mechanics that, this value is third, right? But remember all the time we are talking about uniform, beam, for example, in the depths of the paper, right? So in other cases, for example, in this case, it doesn't have to be like, it doesn't have to be uniform like this. Let me give you an example, so just to at least understand this. Same thing, let's say. And this is a free surface. Okay, call it H. Okay. And let's look at this surface, and imagine now I have sorry, I don't have a space to make a circle, but just whatever the surface is. Okay, so if I look at this, and then I have this surface. Distribution, do you think the distribution will be different of the pressure here? Anyone? No? Why? Do you think the distribution will be different from this? Yeah, same as last example, right? Because this is, this distribution here is a function of gamma, right? So this pressure at any point here, this pressure is gamma, H or something like that, right? So gamma is constant, right? It's for the same fluid, this same fluid. As you go down, you will have a, more, right? So if you look at this, okay, so where is the center of area here? Is it in the middle? Center of the circle? Okay, no. Look at this. So we agree that that's the only part of the area that we are interested in. This part here is non-relevant, right? That's the only area that we are interested in. Why? Because this is the area where the fluid is acting, right? I hope you guys understand what is this I mean. Huh? So we're looking from this side here. So we're looking at this surface, and the surface here is just like, circular. It doesn't have to be a circle. It could be just ellipsoid or something, right? So when we look at this, we're looking at this area. So where is the center of area for this? Again, center of the circle. Do you think this is the center of the circle here? No. Of course, the middle line. I like that. Okay, let's assume, okay, this is symmetrical. So let's agree. This is the line where the point that we're looking for is. Yeah, I agree with that. But do you think this will be at the middle? Do you think this will be at the middle of this? No, right? It's going to be like somewhere here, right? Just going to make, right? Because basically, right, the center of the area will be somewhere. We don't know what is the value of this CG here, right? And the pressure will be a little bit lower here, right? And the forces will be here, right? So what I meant here is you have to look at what is the contact between the fluid and the surface. So apparently this is not a circle anymore. This is the area that we are interested in. I don't care about the surface. I care about the contact area between the fluid and the surface, right? And this area now is, yes, it's symmetrical on around the vertical axis, but it's not symmetrical at the horizontal axis from the center of gravity, right? So we have to find out the center of this gravity, and then, or it's the center of the area if this is a uniform material, and then find out the pressure, center of pressure, and find out the total resultant force. Why I'm doing all this? Just to an introduction to general concepts as we can see here, right? So if I have a surface now that is inclined, okay, so I can do whatever I want. I can do like, this pressure distribution. If this area is non-uniform, right, I can actually go step-by-step analysis. And somebody in the chat was mentioning about integration in the beginning of this discussion, that if we have an element of this surface, and we call this element is dA, right? I can take like, for every single point on this surface, remember this, I'm looking at in this direction now, right? So this is the surface I'm talking about. If you're looking at it from this direction, I see something non-uniform like this, okay? And if I take an element on this surface, right, I will find out the area of this element. And now I look at, what will be the pressure at this point. You see here, this point here, which is here, depend on this H, the pressure here is equal gamma H, right? So I can basically look at the pressure at this point is gamma H, right? The area of this point is, let's say, for example, an element that is dx dy, and this is dx, right? And then I look at, the summation of, like, based on, remember, the force will be the integration of b dA over the whole area, right? So I can basically take all these elements, remember, and then, in your mass course, when we are talking about the moment of the area, we take the moment at any point of these total forces equal to the total resultant force times the distance between the center of moment and the center of force, right? Or right? I will explain this in a few seconds. But again, this surface could be any shape of any surface, right? And it could be inclined at an angle theta, okay? It doesn't have to be vertical, it doesn't have to be horizontal, it could be at any direction, right? So in this case, we can basically find out the pressure distribution. So let me ask you questions. So if I have a surface like this now, Okay. And I have a surface like this. Okay, and this is your free surface. So the pressure here is 0. Okay. What will be the pressure here? Let's say, for example, a point A. If this is H, what is the pressure here? Rho GH, right? Simple, right? And when it's acting on the surface at this point. What is the direction of this force? What is the direction? Down? What do you mean down? The pressure at the surface. This is the surface here. What is the pressure direction? I'm talking about force here. Okay. What is the pressure force here? What is the direction of the pressure force? Guys, don't disappoint me. X direction, right? Oh my God. The pressure force is a normal force to the surface, right? Do you agree that the pressure is a normal stress? So all the time when I ask about direction of force, it has to be normal to the surface, okay? So in this case, I have a pressure force here, right? Equal this value. How about at point B? More, less, more, right? What is the direction? Normal, right? So it's gonna be something like this. I know some of you thinking about like, is the fluid from one side or the other side? Okay, let's assume there is no fluid here. I'm talking about the surface. The fluid is in touch with this surface here. Okay. So fluid is only at the top of this surface here. Okay. How about point C is more? How about point D? If this is H. It's increasing until we reach to the maximum point here. So if I plot the pressure distribution, it's something like this. I am sure some of you remember the superposition. You remember this, like, you know, you cut this into two and then remember these kind of things in mechanics? Anyone remember this? Okay. But look at this point here. It's not 0, right? It's some value here, which is depend on this H, but it's a more value here, right? So at the end here, the total resultant force will be somewhere here, right? This is F total, okay? And if this is your center of area, CG, right? If I look at this surface from this direction here to be something like this, and this is your CG, right? And this is the pressure center, CP, right? So this will be your CG, the center of gravity or the center of the area, and the pressure will be a little bit lower here by a certain value, right? I don't think we have, we have no time to really go over a derivation of, what will be the value at the end for these pressure forces. But I'm going to remind you a very important thing that the rule that we did was when we have a variable forces acting on a beam or a surface, like in mechanics. We took the element of these pressures and we take the moment, of these forces. If you remember, you have small little forces acting on a beam, and you need to find out the total resultant force. What did you do? You take a moment at some point, right, for all these forces, and you say that the summation of moment of all these forces equal to the moment of the resultant force or the total force around the same exact point. So this is the same exact, analysis that we do here. At the end, we can find out what will be the resultant force that we are talking about. Okay, and this resultant force we found out from this derivation that it's equal to the pressure at the center of gravity of right, or the center of area times the total area. Very simple. Okay, so this resultant force is equal to the pressure at this center of area times the total area. Okay, so, and it's going to be acting a little bit, of course, this is a non-uniform shape, right, like this. So the center of pressure could be far from the center of area in the X and also in the Y direction. And that's why we develop a relation for the location of this center of pressure forces. Yes, Marcus, I guess it's all depend on how the surface is uniform or non-uniform. We're trying to kind of generalize the idea, and then once we have a uniform shape of this surface in the normal direction of the paper, we can apply same kind of principle that we learned in our mechanics course, right? So I agree with you, right? It's only one condition, that it has to be a uniform surface in the depths of the slides, right? So we have to keep in mind something like this. So now it's becoming a very simple problem. We just need to find out the center of gravity or the center of area. Of course, we are talking about, let's say, for example, most of the time, that's not our topic for the fluid mechanics to complicate the center of gravity and other things, because this is kind of a given for you. Of course, you can make the problem as much complex as you want. But, most of the time we are dealing with uniform surfaces, circle, like, rectangle, square, something like that, okay? We need to find out the center of this area, right? Or the center of the gravity, if you want to say, right? For the area in contact with the fluids, right? And then find out the pressure at this point and multiply by the total area of the surface in touch with the liquid. Of course, the pressure is equal gamma H, right? So if you find out these points, you can find out the vertical distance of this fluid from this point to the free surface, and find out HCG, and then multiply by gamma will give you the pressure. Okay. Remember here, when we studied this part here, there are some inclination for this surface in general, because we don't have vertical or horizontal surface. You might have surface that is inclined with theta, right? And we can find out the distance along the surface instead of like the distance that is vertical. And what is the relation between this inclined distance and the vertical distance? It's basically sine this angle. So xi here is h over sine theta. So if you know the inclined distance of the surface, you can find out the vertical distance by sine theta relation. Okay. So it is becoming a very simple problem now. We just need to find out the center of area of the immersed surface, or the surface in the depths inside the fluids, and we need to find out where the center of pressure is located. Okay. Same thing that we did for the forces. If you remember in your mass, when we need to find out the center of area, we start introducing something called the second moment of area, right? Which is basically what we refer to as Ixx or Iyy. This is basically a general relation, which means that this point doesn't have to be along the CG. It could be a little bit far in the depths this way, and also far in this direction. So it can be, going this way and also in this way. Okay. So the distance between the center of the area and the center of pressure is minus. Why minus? Because it's all the time is lower, right? It's going down because the fluid, pressure forces will increase as you go down. That's why this sign, minus sign here is giving you, the direction that is going down in the fluids. It's gamma sine theta, the second moment of area divided by the pressure at the center of the area times the area. Okay, same thing here, right? But the center, the second moment of area here, remember the second moment of area, if we are talking about something like this, so it's all depends, right? This is your XX, this is your YY, right? The second moment of area around XX is completely different from the second moment of area around the YY, right? If we have a uniform surface, it's going to be the same, right? Very simple type of analysis. Like if you have, for example, a square, is going to be like, same in both directions. Okay. Any questions so far? Yes, you are right, Dozy. Yeah, this is why. I copied from the textbook without even noticing it will make these kind of mistakes, right? Okay, so the equations say, yeah, okay, so done. Of course, if you guys remember in your math course, you can find out the second moment of area from tables like this. Of course, all these type of equation, you don't need to memorize it. It will be given to you, right? So all these equations, don't have to worry about it. So it will be given to you, so you don't have to remember all these kind of, relations for the second moment of area and so on. Okay. So let's look at a problem, at least to understand the complexity of these kind of, application when we are looking at, a problem like this based on the knowledge that we just presented today. Okay, it's a very simple thing. You just need to make sure that you understand the concept of the pressure. You understand the idea that the pressure is going higher on the depths. You need to understand how these surfaces in contact with the fluids, and then imagine, what will be these pressure forces and so on. Okay, so let's look at this problem here. We have a tank here, and this tank is, let's say, for example, there is an opening inside this tank, and this opening here is, let's say, this is a gate here. Okay, and the gate, imagine this could be a small little opening, and this opening is said, like, this gate AB is 1.2 meter long and 0.8 meter into the paper, right? So look at this, which means that if I look at, so it's basically what? This is my gate here, right? So the distance here is 1.2, and the distance to the depth of the paper is 0.8. Okay. And this is basically a nice uniform rectangle, right? So, okay, neglecting the atmospheric pressure is actually, I don't like this. I'm just copy this from the textbook, but is neglecting the atmospheric pressure here is not the right word for it, but it actually means that we are looking at gauges, right? So we're looking at, a reference from the atmospheric conditions. Okay, he's asking about a force that apparently this force is acting on this direction. Okay, and this force is far from this edge here by a distance x. Okay, you need to find out, compute the force F on the gate and the center of pressure, right? So he's basically referring to the pressure force coming from the fluid. Okay, so let me add to this. This is an example in the textbook. Compute the hydrostatic force. Because this is a force that is coming from the fluid. Okay, so let me ask you a question now. Where is the center of gravity or the area for this? Some people are asking, okay, let me answer your question in just a few seconds. When we so we have one fluid here, and this fluid is like this. We're going to talk about other type of fluid and also other, problem that doesn't have a free surface. It might be a pressure added to this. Okay, so let me ask you a question here. Where is the center of gravity for these gates? We have to agree that we don't care about all these surfaces, right? These surfaces, we're only concerned about this gate here. Where is the center of gravity? Coordinates. Okay, what do you mean by the coordinate? Yeah, so here I can say that this is your center of gravity or area, right? Which is basically here, right? So it is in the middle of this, right? So you agree with me? So basically, because this is a uniform gate, right? So the point at point G is basically, the center of gravity and the center of the area, because nothing mentioned about that this gate has an non-homogeneous material or anything. It's just simple uniform gates, right? So let's say, for example, now I need to find out the center of gravity. What will be the value here? So first of all, what is this distance here? Anyone? Anyone? You see here, this is 1 meter, and this distance here is half of this. So it's 1 point, and this is 0.6, which means that I have a triangle here that is this is 1.6, and I have an angle here that is 40 degrees. So I can find out this L here, right? So what is L here? So sine 40 is equal to L over 1.6. So I can find L here as 1.02. Okay. Why I'm interested in this? 1.6 sine, is that correct? Not sure. I have it calculated here. Yeah, okay. So I don't know. You just check the number if it's correct or not. Okay, so now I have L here, and this is a point G, right? What is the force that we are talking about here? The force here is the pressure of these points, right? CG or right, times the area. Okay, what is the pressure at point G? Some people asking about this distance here. Guys, this is point This is 1 meter. This is 1.2. So the half of this is 0.6, right? So this distance here will be 1.6, right? Okay. So what is the pressure at point G here? It's gamma times, right? Okay. You have to ask this very important question. Okay, when you are basically referring to this distance here all the way, right to the free surface. Is that the free surface? Is that the free surface? Why you say no in this problem? I like that. I actually like it, right? But is there any mention about a pressure added to these? So you are filling the tank until you maximum the tank, right? So there's no, additional pressure added to the tank, right? I agree with you that every time you have a closed tank, you have to ask yourself if this closed tank is subjected to a pressure or not. In this case, it's not subjected to additional pressure. There is no any gauge indicating that there is a pressure at this point here, right? And it's telling you that neglect the atmospheric pressure. And in this case, he's basically assuming that this tank is filled to a certain point and there is no more additional pressure added to it, right? So I like the way that you guys think now, right? Some people are asking about if I have multiple fluids at the top of this surface. Remember how to find out the pressure at a point in the fluid? Remember? You just need to, the pressure at the top plus gamma H plus, gamma H1 plus gamma H2 until you find out your pressure at the point that you are looking at, right? So whatever the problem is complex, you can make it, easier by your understanding of the concept of this. So you just need to find out pressure at point G, and apparently point G is far from this point here, or we can call it the free surface in this case, by a distance equal to L plus the 4 meter, right? So simply, I can say that now the force here is BG or CG times area, BCG here is gamma times H, and H here is this L plus the 4 meter. So it is, this gamma here is, remember, the oil here is given as a specific gravity of 0.82. You remember gamma oil, sorry. Gamma oil will be gamma water times the specific gravity, right? Times L 1.02 plus 4 meter, right? Specific gravity here is 0.8. Specific weight of the water is 9810. 1.02 plus 4. I can calculate this as 39.4 kilonewton. Sorry, I didn't calculate the pressure itself. I think can you calculate this for me? I don't think this is the right number. Anyone can calculate this for me? Because I only have the force. Okay, anyone? Ethan? You guys confirm this number? Okay, another number now. Anyone? Just calculate this. Okay, 39.4. Okay, all right, okay. So 39.4. Remember, this is the basic unit, so it's a Newton per meter square. I guess kilonewton. Divide by 1,000, so it's kilonewton per meter square. Okay. What will be the force in this case? The force will be this PCG times the area, and the area here is 39. 0.4 times the area here. What is the area for this? What is the area for this gate? The area of the gate is given at 0.8 times 1.2, right? So I can 1.2 times 0.8. So I can calculate the force now. Anyone calculate the force? I don't know what is 0.96 M. I don't know. Oh, the area, okay. Now you can calculate, the force as 37.8. Did you guys confirm this? So this is the force, right? So this is the force. Now, what will be the center of? We agree that this force here will be a little bit lower at this point. So if this is G, point B will be a little bit lower, right? So what is this distance here? Remember the CB distance, right? Okay, how we calculate this CB distance, remember? So we have the CB distance here is minus, right? I, right? Remember this equation? I don't even remember now. So minus I, or the distance here is I sine over the BG, right? So this is what we have here, right? And sometime we are using the B, or if BG over the gamma, it will be basically H, right? Because you can put this at the bottom, 1 over gamma. So B over gamma is your HG, right? So you can calculate the area here, which is the I. And, when you are looking at the solution, they are not putting the sign now because they are assuming that you understand that this is going to be lower as we put it here, right? So the distance, exact absolute distance here is I, sine over HA. Yeah, so I have this. So when we are looking at HG is basically what? It's BG over the gamma, right? And the area, IXX. I like always to put it this way. Why? Because sometimes you know what is the pressure at point G. You just need to divide it by gamma. So you don't have to worry about like if there is multiple fluid at the top or anything. You just find out the B at point G, divide by the gamma where the surface is, right? In this case, it's just one oil all the way, right? And this is the area of the surface. How can we determine I here? Right? Ask yourself if this force here is doing like this, like, is acting on this surface. Where is the inclination rotation of this surface? The surface will be basically like this, right? As if the surface will rotate like that. Okay, so in this case, we have this distance times this distance cube, right, divided by 12. This is the I that we are getting for a rectangle like this, right? So I can find out this I here as so the distance is 0.8 times 1.2 cube over 12. This is your X, right? So I can find out this is CB as, can you calculate this for me? I think I didn't calculate every single piece specifically, but can you calculate this I for me? 0.1152, and I can find out this one here is sine, and here we have an angle of 40 degrees times 0.1152 divided by the pressure at point G, which is 39 points. Okay, 0.4 divided by gamma, which is 0.8 times 9.81, because this is a kilonewton, this is kilo as well, and the area here is 1.2 times 0.8. So I can find out this distance here, and the distance here is 0.0153 meter. Okay, so what is telling you here that I have something like this. This is your G or CG, and a point that is a little bit lower here, and the distance here is 0.0153. What he's asking in this problem, he's asking about the distance here, this X here. So apparently X here is half of this, right? So it's 0.6 plus 0.0153. People gonna put a sign here, negative at the front of this, sorry, negative at the front of this part here. They understand that the point will be on the lower side. That's the only difference for this problem. So you can basically calculate X as 0.615 meters. You don't need to put, like, you know, 3 digits is enough, right? So, okay. Any questions on this? I think we are spending. Shouldn't sign be? I don't know. Just guys, you guys calculate this, like, you know, spend time calculation. I'm not gonna. Any issue is the way that we are solving the problem. In real life, what do we find? Yeah, let me add to. Okay, but so far, like, did we find out this F? Okay. Okay. Any question about the steps, how to find out these static forces? Any questions on that? You guys, do you have any questions on this? Finding the force and finding where these forces acting? Are you guys still around? Do you hear me? I don't know. Okay. No questions. Okay. So what happened if I find out this F now, right? So imagine now I'm, you know, let me add an example here. Imagine I have something like this now. I have this force here. I have this opening. I have this gate here. Imagine, right? And this is a surface, and now I have this force now. I know the value, right? Value. Magnitude value, and also the direction, line of action, right? So it's normal to this, right? Line of action. And this is a gate, this is a wall, and this is a gate, right? And I want to keep this gate closed, right? So I need F here, right? So what will be the value to keep the gate closed, right? And imagine I have a hinge here, something I can open this or close it, okay? So what will be the F here, right? Where is the liquid? The liquid is here. Same problem as the one before. I'm just adding to, right? So now what will be the F here, right? So I need first to find out the hydrostatic force from the fluids, right? Friction. What friction here, guys? There is no friction here, right? What friction here? No shear forces. This is hydrostatic fluids, right? So what will be the force here? What will be the value of the force? It looks like the lecture will be done in 10 minutes. I didn't finish like 20% of the lecture. Anyway. Yeah, so we have to say that, for example, here, in order to keep the gate closed, right? There is going to be a minimum force here. Right? Because of course you can add much more forces F here, right? Just to keep these gates closed, because in normal case, this gate will be opening like this because of the action of this force, right? But you want to have like some other force, you know, acting on the opposite direction here that is creating a moment that is closing the gate here, right? So in order to find out this force, for example, in this case, in a real application, you will take the summation of the moments around zero will be equal zero, right? Let's say point, let's call it point A here, right? And this is basically the hinge here, right? So in this case, I can find out the summation of moments by, I know this distance X, right? So I know basically, let's call this is a positive direction. So it's F times X minus F times, we know the gate here, the whole distance here is 1.2. So this is 1.2. This is equal 0. I can find out your F value here, right? So all the time when you are looking at forces on the gates, you know, same problem can be presented in a different way. Maybe you have a motor here, right? And this motor is applying a certain torque to close this. There's no force here, but you have a moment here or a torque here, right? What will be the engine or the motor that you put at the hinge in order to keep the gate closed? Similar way, right? You just need to find out the torque that is opposing the opening action of this force, right? So most of the time for this kind of application, we need to find out the force on these surfaces. And then we take the forces here and try to, you know, get to the second step of a design problem. Either, you know, finding out forces, either like even finding the material that you are looking in order to build this surface, right? So finding the force or the pressure distribution and the force distribution will allow you to maybe deal with other part of the, you know, the topic that you studied in your mechanics and other design courses. But understanding first the concept of hydrostatic pressure forces will allow you to go to the next step of any design problem. So it could be material selection, could be like, you know, thickness of this surface in order to prevent, you know, bending, for example, and stuff like that, right? So this is a kind of, you know, direct application for these kind of problems. Now, if we go for a, you know, a little bit different than the flat surface, if we go for a curved surface like this, okay, let me ask you a question similar to what we did before. I have a free surface here, and this is a curved surface, okay? What will be the force here? Let's say, for example, here, this is X. What will be the pressure forces here? This is a fluid from this side, no fluid on this side. It's rho gx, right? So I have a pressure force here that is basically, you know, it could be here, that is rho gx, right? when I go here, this is point A, how about point B? How about this first? Let's go point B here. Same thing, right? So rho G H, right? What is the direction of this force? Right. Oh my God. Normal to the surface. Don't forget this, right? Normal to the surface. How about here? More, but normal to the surface. How about here? More, but normal to the surface. How about here? Maybe more, but normal to the surface. You see the distribution here, right? It is because of the, the surface is already curvature, right? So the variation of the distance is, as you go down, is not the same value, right? It's, it's not a vertical distance, right? So in this case, we have a value of the forces, of course, it's a function of the gamma of the fluids. But the problem here, it is not acting on a flat surface. So in this case, we have a resultant force that is, in this case, could be something like this. This is a resultant force or the total force. Okay. So this total force here, I can say that, for example, in this case, could be divided into two components, right? We know that the total force or the total component that is, angled by any, angle like this, right, can be presented in two components. One is horizontal component and one is vertical component, right? So for a curved surface, I can develop a relation for the total force that is acting on a curved surface into two parts. One part is the component in the horizontal direction and the component in the vertical direction. And if I know the horizontal and vertical component, can I know the resultant, the total force from your mechanics? Of course, right? The total force will be, anyone? F horizontal square plus F vertical square, and then you take the root square for the whole thing, right? So you can find out the magnitude, right, for this force. And also you can find the inclination, right? Tan inverse of F vertical over the F horizontal. Similar way that we look at, an angle force or angle total force in terms of its components in the X and Y component. So looks like I have only 2 minutes here, but at least I want to conclude here by giving you an idea that for the curved surface, we imagine that we have, a projected component. So we look at this surface in this direction. So to find out the horizontal component, we look at the surface and find out the projected area. So if we have this is kind of like, okay. So in order to find out the horizontal component, we look at the surface in this direction and imagine this surface now becoming a flat. So we look at it, whatever the surface is, when we look at it from one side, we project this surface over, surface here, right? So we call this is basically the projected surface, and deal with these as almost the same way as we did for a flat surface. We get like, this is a point of G, this is a point of the pressure. We'll find out the force here, and this will be our horizontal force here. So only finding the component separately, this will allow you to find out one component of the resultant force. Okay, I'm gonna stop here. I don't want to rush it, but again, can you help me next time be more interactive and quick, because we need to finish this chapter next time, because this is kind of an extended time for this we are spending here. I hope also the tutorial already started introducing this concept. I'm not sure which group is taking the lab and the other one is doing the tutorial. So we'll try to finish the hydrostatic chapter or the fluidostatic chapter next time. Any questions on this? The distribution, yes, the distribution will be basically going with a curvature. Yes, that's correct. The thing now is like we don't want to get into the idea of looking at the small little forces distribution. We want to get like the total resultant force. Okay, so as if we imagine that we are integrating all these small little distribution of forces over one big component that is inclined in a general direction. So now we are dividing this big component into a horizontal one and a vertical one. And if we know the horizontal parts and we know the vertical parts, we can find out the total or the angle of this resultant force. Any questions? I'm going to stop recording here. So if you guys have questions, we can stop recording.